Welcome to this explainer. Today we're breaking down the dynamic, constantly shifting world of coastal landscapes. If you're looking to master the interconnected coastal system model, well, you are definitely in the right place. Let's jump right into the geomorphic processes that break down, transport, and rebuild our shorelines. We can organize this continuous system into 5 distinct categories: weathering, erosion, mass movements, transportation, and deposition.
Section 1, Weathering. This is all about in situ rock breakdown.
So what exactly is weathering? Simply put, it's the process that uses energy to produce physically or chemically altered materials from surface or near-surface rock. The absolute crucial takeaway here is that weathering happens in situ, which literally means exactly where the rock stands. There's no moving force carrying the rock away. It just sits there and weakens the cliffs, providing the essential raw sediment for the entire coastal system. Breaking it down, we have 2 main types of weathering. First, physical or mechanical processes, like freeze-thaw and salt crystal growth. These literally exert immense pressure to fragment the rock, but without changing it chemically. On the flip side, we have chemical weathering, things like solution, oxidation, and hydrolysis. These processes actually use chemical reactions to alter the rock's mineral composition, basically decaying it into brand new, weaker substances. In textbooks, these processes are often neatly divided up, but out in the real world, say on a stretch of weathered limestone in Dorset, physical, chemical, and even biological weathering, like plant roots or burrowing animals, are all acting simultaneously. It's like a giant team effort. They work together relentlessly to weaken those coastal rocks, prepping them for the next stage. Which brings us to Section 2, Erosion. This is where we get into active coastal wear. Now, if weathering is in situ, erosion is all about movement. Erosion is the active wearing away and removal of rock by a moving force. And on the coast, you guessed it, that moving force is almost always the energy from breaking waves. That is the distinct line you need to draw here. Weathering weakens, while erosion actively removes. Let's walk through these specific marine erosional processes. First up, hydraulic action and cavitation. That's the sheer brute force of moving water and compressed air smashing into cliffs. Next is abrasion, where waves pick up sediment and literally hurl it at the rock face like giant sandpaper. Then there's attrition, which happens when those individual sediment particles collide with each other out in the water, getting smaller and rounder over time. And finally, bioerosion, where marine organisms actually bore right into or graze on the rock itself. To really grasp the sheer scale of energy involved here, just picture high-energy waves absolutely slamming into a cliff face. That is hydraulic action in a nutshell. When these massive waves hit, they trap air inside the rock's cracks. As the wave pushes forward, that air is heavily compressed, creating extreme pressure that can reach a staggering 11,000 kilograms per square meter on the rock face. Then, when the wave retreats, that pressure releases explosively. This causes cavitation, acting like giant hammer blows, just shattering the cliff from the inside out. Moving on to Section 3, Mass Movements. This is where gravity completely takes over. Essentially, a mass movement is the downslope transport of material under the direct influence of gravity. It doesn't really need a moving agent like water or wind to carry it. Gravity is the main driver here. And it usually acts on the exact same material that was just weakened by all those weathering processes we talked about earlier. To really get a handle on this, think of it as a delicate balancing act between 2 forces: shear strength and shear stress. Shear strength is the internal resistance, basically how well the rock holds itself together. Shear stress is the downward pull of gravity and weight. This dynamic creates what we call a safety factor. If shear strength is higher, the cliff stays put. But the very second shear stress takes over, say after a heavy rainfall adds a ton of weight and lubrication, bam, mass movement begins. When we classify these movements, it really comes down to 2 main factors: speed and water content. Imagine a scale. On one side, we have speed, ranging from an incredibly slow creep to insanely fast slides. On the other side, we have moisture, ranging from bone dry to completely saturated. By looking at these 2 factors together, we can figure out exactly why a collapse turns into a fluid mud flow, a rapid dry rock slide, or a slow, barely perceptible soil heave. The actual physical structure of the coastline dictates exactly what kind of collapse is going to happen. For instance, a steep rockfall is super common on bare, unvegetated rock faces, where blocks just detach and plummet straight down. But with a rock slide, the rock often has angled lines, seaward dipping bedding planes. Once weakened, huge, intact sheets of rock just slide right down those tilted layers and crash into the sea.
All right, Section 4, Transportation. It is time to get this sediment moving. But before sediment can travel anywhere, it actually has to be picked up. That brings us to a crucial concept, entrainment. Entrainment is simply the process where particles are lifted from a stationary position by a flow of water or air. Think of it as the critical energy threshold needed just to get the sediment moving in the first place. Larger particles obviously need a massive surge of wave energy to be entrained, while fine sand, that requires much, much less.
Okay, so once the sediment is entrained, it travels in 4 distinct ways, mostly depending on its size. First is traction, which is for your heavy boulders and cobbles. They are literally rolled or pushed along the seabed. Then we have saltation, which is a bouncing, skipping motion for medium-sized sand grains. Next is suspension. This happens when finer particles, like silts and clays, are carried completely afloat within the turbulent water. And finally, solution, where completely dissolved minerals are carried invisibly in the water mass itself. Let's zoom in on saltation for a second. Imagine a sand grain moving in an arc-shaped trajectory. It gets entrained by turbulent water or wind, travels a short distance, and then drops back down. The really interesting part is that when it lands, it impacts the seabed and disturbs other grains, kicking them up into the current. It creates this continuous cascading chain reaction of skipping sediment all along the coast.
And that brings us to perhaps the most famous transportation process of them all, longshore drift. When waves approach the shore at an angle, usually driven by prevailing winds, the swash carries sediment up the beach at that exact same angle. But the backwash flows back straight down the slope, moving perpendicular to the sea under the force of gravity. This repeating, relentless cycle creates an irregular, zigzag net movement of sediment all the way down the coastline. Finally, we've arrived at Section 5, Deposition. The building of the coast.
Deposition is simply the direct result of energy loss within the system. It happens when moving water or wind slows down, basically losing velocity or volume, and it just no longer has the energy to carry its load. So what does it do? It drops it. Geomorphically speaking, deposition takes place wherever the rate of sediment accumulation actually exceeds the rate of removal.
There is a very direct relationship here between particle size and settling velocity. As you might guess, the larger and heavier a particle is, the more energy it takes to keep it suspended. So as a wave or current starts to slow down, those massive boulders are the very first things to be deposited. As the velocity continues to drop, smaller and smaller pebbles fall out until finally only the absolute finest sand and clay are deposited in the calmest waters.
And speaking of fine clay, there is a fascinating chemical process that happens here called flocculation. Fine clays are so incredibly light, they can stay suspended in fresh river water almost indefinitely. But when that fresh river water meets salty seawater in an estuary, a reaction occurs. The electrical charges in the salt cause those microscopic clay particles to clump together, to flocculate. They become heavy enough to sink, which is exactly why estuaries are characterized by those vast, deep mudflats. We have covered a tremendous amount of ground today, from weathering and erosion all the way to mass movement, transportation, and deposition. But here's a final, provocative thought to leave you with. How do these 5 distinct, incredibly powerful processes combine and interact out there in the real world to sculpt the specific landforms, the massive sea stacks, the sweeping spits, the towering cliffs that you'll be studying next? Keep that question in mind as you move forward. Thanks so much for tuning into this explainer.